Welcome for today's seminar. Today we have Dr. Rishabh Roshan from University of Southampton. He's going to talk about gravitational waves to investigate early universe. Please go ahead, Rishabh.
Yeah. So first of all, I would like to thank the committee for giving me the chance to present my work. Today I'll be discussing how we can use gravitational wave to see the early universe. Mm, So let me briefly, let me briefly introduce myself. Uh, uh, I'm Rishabh. I finished my PhD in 2021 from IIT Guwahati, where I mostly worked on dark matter, baryonic symmetry, and neutrinos. Thereafter, I was in PRL for a brief amount of time, and after that, I moved to South Korea for my postdoctoral position. There, I started working on primordial black holes, cosmic strings, and how they can generate gravitational waves. After finishing my postdoc in South Korea, I joined University of Southampton, and here my main focus now is on gravitational wave, and I've also started working on other gravitational wave sources like domain wall, and now I've also started working on phase transition. So this is the plan of my talk. I will briefly introduce how we can see the early universe, what role does gravitational wave play in that. Then I'll go, I'll discuss some of the cosmological puzzles in the early universe, followed by I'll go into the detail of how gravitational waves can be used to see, basically how gravitational waves can be used to see the early universe. And later on, where I'll discuss some of my contributions that I've done in this direction, and then I will discuss the current status of the phenomenology, gravitational wave phenomenology that we do, and some of my ongoing works, then future direction and outlook, the synergies with the physics department, and then finally I would conclude. So, our understanding of early universe has increased many folds in last couple of decades because we have started using different cosmological tools like we have studied the photons present in the present universe, and that took us back to the recombination era. Similarly, one can get an access to the era after BBN with the help of neutrinos. But the important question one can ask is that can we probe or can we delve deeper into the universe? So the answer is yes. The answer is yes. We can actually use gravitational waves to see the early universe, as you can see from this picture on the right. The gravitational wave does not basically interacts only through gravitation through the gravitationally. It just has a gravitational interaction, and as a result of that, it travels freely. So it can tell us about the early history of our universe. So also just feel free to stop me whenever you want. I mean, if you have any question. Yeah. So now what gravitational wave is? Gravitational wave is nothing but just a ripple in the fabric of space-time. So if we just consider, or if you look at the Einstein equation, what it suggests is that space-time determines the trajectory of all the objects, or in other words, a massive object will curve space-time. Now, if we consider a small fluctuation around the metric tensor and substitute it back into the Einstein equation, is what we get is the propagation of gravitational wave in the vacuum. So if we look at this equation, on the left hand side we see the gravitational wave amplitude, and on the right hand side we see the source that produces the gravitational wave. Now, if we consider a far field regime, so by far field regime, what I mean is that when the source is far, far away from the observer, one can approximately write the amplitude in the following manner. So here, as you can see, on the right side of this equation, we have G, which is the gravitational constant. R is the separation between the R is the separation between the source and the observer, and Q is the quadrupole moment. So the moment we see this quadrupole moment appearing, the first question that comes to our mind is what happens what happens to the monopole moment, or why not dipole moment appears into the picture. So if we just do a multiple expansion of this stress energy tensor, what we find is that due to the conservation of mass, the monopole moment vanishes because monopole tells us about the total mass of the system. Similarly, because of the conservation of momentum, the dipole moment vanishes as it tells us about the center of mass of the system. So the term that contributes to the gravitational wave amplitude is the quadrupole moment. So what quadrupole moment is? Quadrupole moment tells us about the distribution of mass in the system. So, for example, if we look at this picture, what we see here is a black hole eating a giant star. So, as you can see, the mass distribution is changing. So, in order to generate gravitational wave, what we want is that there should be a change in the quadrupole moment as well. So, a static quadrupole moment or a static distribution of mass won't generate gravitational wave. That's why this term comes with a derivative, and this suggests that the source cannot be static. Additionally, as the distance between the source and the observer increases, the amplitude will decrease. Now, once we have information of the amplitude, gravitational wave amplitude, we can calculate the power. So on the right hand side, I just show the timeline of all the significant events in the history of gravitational wave phenomenology. Next, why should we pay so much amount to construct the gravitational wave experiments? The answer is
So,
that science.
so
Yeah.
Rishabh had a question
Yes.
regarding our earlier slide.
Yes.
So here you are mentioning this is all in weakly coupled system where your metric perturbations are very small.
Yeah.
But
Yes.
you're mentioning that you can use gravitational waves to probe early universe. So how early can you go with this formalism?
Yeah, so this is just an approximation. In the later part of the slides, I'll show that the gravitational. I'll try to show that we can also probe gravitational waves that were generated during the reheating, that were generated after the reheating. So I'll discuss all these things in the later
And
slides.
what is the analog of this? What creates these kind of quadrupole moments in the early universe? Are you also going to show those?
Yeah, I'll briefly discuss those things. So the thing is that, like, for example, if a PBH evaporates, it basically the PBH just. I mean, this is just an example. A PBH distribution in the universe is inhomogeneous. So what it does is that it creates isocurvature perturbations, and when it evaporates, it releases energy in the plasma. That means the isocurvature perturbation is actually transformed into the curvature perturbation. And in this process, what it does is that it generates quadrupole moment. This fluctuation, when PBH evaporates, it generates quadrupole moment, and hence the gravitational wave signals are also generated. So this is just one example. I'll show how the quadrupole moment can be generated in domain wall and
But is
in
it statistic because there can be backcoupling of the radiation on the object. So how are you sure that it will remain as a quadrupole even with this primordial black hole evaporations? You know?
Yeah, that's a good question. But the thing is that, like, when we talk about this early universe and gravitational wave, we need to work under certain assumption, and here we consider that those back reactions are very small, so we
Yeah,
kind of
my
neglect.
concern is that at that
Mhm.
time many of these assumptions may fail. So
I
are
completely
you
agree. Yeah,
maybe you will tell us more about it, right?
yeah, later, yeah,
Okay,
in the
sure.
later part of
Yeah,
this slide.
please go ahead.
All right, thank you. Yeah, so as I was saying, that the scientists have done incredible job of detecting the gravitational wave signals. For example, the first detection took place. The first signals were discovered in around 2015 by LIGO Virgo collaboration, suggesting that the source of the gravitational wave was a merger of black holes. Now, the recent discovery by the PTA projects, or basically the Pulsar Timing Array project, also reported a positive evidence of stochastic gravitational wave band. So the interesting thing about this spectrum was that it was in a very low frequency region, around nanohertz or so. So this suggests that the source of the gravitational wave might be a merger of supermassive black hole binaries, or it might have a cosmological origin, or it might be a combination of both. So moving back to the next slide, here I just show different experiments uh, that are currently running and also some upcoming experiment. And I just want to show that there are several experiments working in this direction, like the ground-based experiment, like LIGO, Virgo, ET, and the upcoming LIGO India project. Then we have upcoming space-based observatories like LISA, BBO, the SIGO Mu arrays. Then we have pulsar timing arrays, and all. If we look at these experiments, we notice that all these experiments works in a different frequency regime. That means that these experiments, if they detect any signal, that they can actually give us some idea about the early universe. So, so this is the sensitivity curve of the current and the upcoming gravitational wave experiment. And as you can see, it covers a huge range of frequencies starting from nanohertz to kilohertz. So this was all about a bit about the theory and some discoveries and some detectors of gravitational waves. Now let me tell about briefly about some of the cosmological puzzles that are present in the early universe. For example, what we know is that after the discovery of Higgs boson, the standard model particle spectrum is completed. Um, and we are also familiar with the success of standard model. But then there are still some unanswered questions like the origin of dark matter. Standard model predicts neutrinos to be massive, but oscillation data suggests the other way around, that neutrinos are massive. Why there exists a matter-antimatter asymmetry? So let me just briefly introduce this issue. So the dark matter, which is basically a cosmological glue because it holds everything together, all the matters in the universe together. So it constitutes roughly around 25 to 27% of the energy budget of the universe. Now, there are several evidences that suggest the existence of dark matter in the early universe. In the universe, like the galaxy rotation curve or bullet cluster. So all these evidences suggest us that the dark matter is massive. It interacts very weakly. It interacts. It has a gravitational interaction, and on the other hand, it is also stable. Why stable? Because it still exists in the universe. Now, what we don't know about the dark matter is its particle nature, how it actually came into picture, what actually are its interaction, what is its mass scale, are there experimental signatures of dark matter. The second thing is neutrinos. As I said, the standard model predicts neutrinos to be massive, but neutrino oscillation data suggests that they are massive and they oscillate among each other. The thing that we don't know about neutrinos is neutrinos are its origin of mass. Is it Dirac or Majorana? What are the absolute neutrino masses? And my favorite is we ourselves is an example of beyond the standard model physics because we exist and we exist because something happened in the early universe. Now, during the course of expansion, I mean, after the Big Bang, both particle and antiparticles were created in the same amount. Now, during the course of expansion of the universe, something happened and all the antiparticles vanished. We don't know what the reason was. So and that's the reason why we exist. So this particle-antiparticle asymmetry is quantified by this number, which is around of the order of 10 to the power of minus 10. It is just the ratio of the number density of matter to that of the radiation. Now, what we don't know is the origin of baryon symmetry. What is the source of CP violation? Are there again experimental verifications of such experimental? Is there a way to detect or way to detect the origin of this baryon symmetry? So this was some. These were some of the cosmological puzzles that we are still trying to solve. Now there are several BSM extensions that actually tries to solve these issues, and the one of the simplest extension is to consider the standard model, which consider the extension of standard model with three right-handed neutrinos. Now, what it does is that if we do that, one can write the following interaction. So you see this right-handed neutrino NIs can couple to the standard model. Let me tell you that these right-handed neutrinos are standard model gauge singlets. So they can couple to the standard model leptons and Higgs. And at the same time, one can also write a bare mass term for the right-handed neutrinos. And notice that like these right-handed neutrinos, this mass sum actually violates the lepton number by 2 units. Now, once the electroweak symmetry is broken, the neutrino can obtain its mass, and it can be expressed in the following manner in type 1 seesaw framework. And you notice that heavier the right-handed neutrino, the lighter will be the neutrino mass, active neutrino masses. And that's why we call it seesaw. And it's just a cartoonistic representation of type 1 seesaw that I show here. Now, what are the key features of type 1 seesaw? Now, the key feature of type 1 seesaw is that even with two right-handed neutrino, one can explain the smallness of neutrino mass. One can do leptogenesis, and it can be done by the CP volatility decays of right-handed neutrino. It predicts that neutrinos are Majorana. It is also connected to the baryon symmetry, and a specific prediction which two right-handed neutrino is that the lightest active neutrino is massless. Now, again, there are some open questions in this direction as well. Like, what actually is the number of right-handed neutrino? Because if we consider type 1 seesaw embedded in a bigger symmetry like a B minus L symmetry, demands three right-handed neutrino. Now, this is an important question about the number of right-handed neutrinos. The next question is that seesaw can accommodate neutrino mass together with leptogenesis, but can it also accommodate dark matter? Well, if it can accommodate dark matter, what is the production mechanism? Now, what are the experimental signatures of type 1 seesaw? So let me now briefly tell you about my contribution or the contribution I've done in this field. So, first, I'll try to show you the cosmological implications of the third right-handed neutrino. By third right-handed neutrino, I mean the one which was decoupled, and how type 1 seesaw can be connected to the reheating era. So, so in this work, what we showed was that if we consider the lightest right-handed neutrino, if we think about the lightest right-handed neutrino, it can actually play the role of the dark matter. Now, how it can play the role of the dark matter? Because in the previous slide, as I said, with two right-handed neutrino, so in a two right-handed neutrino framework, what people generally consider is that one of the third right-handed neutrino is more or less decoupled. So it can be decoupled only if it has a very feeble interaction or if it does not have any interaction. So in order to see that, what you can do is that you can just consider a zero entry in this Yukawa matrix, and this Yukawa matrix is the Dirac-Yukawa interaction that I wrote previously. Now, if we completely want to decouple this right-handed neutrino, we just consider a zero entry. Now, in this case, the right-handed neutrino cannot be produced, and it can only be produced gravitationally. So what we can do is that if we slightly perturb this zeros to a small value, which is epsilon, and as I show you, this epsilon is very small. Now, what we can do is that with this slight perturbation, what happens is that the lightest active neutron also get a very tiny mass. So this means that this perturbation also gets connected to the mass of the lightest neutrino. So as you can see in this expression, that epsilon becomes proportional to the mass of the lightest active neutrino, which I denoted with M1, and and capital M1 is the mass of the dark matter or the lightest right-handed neutrino. And this relation can easily be obtained using the Casas-Ibarra parameterization that I show on left. Now, as a result, what happens is that after the electroweak symmetry has broken, the right-handed neutrino, the right-handed neutrinos will mix with the active neutrino. Hence, the active sterile mixing comes into picture, as you can see. And this active sterile neutrino mixing is expressed in the following manner. Now, as a result of this active sterile mixing, what happens is that the gauge boson, the standard model gauge boson, can also decay to the dark matter, as you can see from this diagram. The standard model gauge bosons like W can decay to the right-handed neutrino through charge current interaction. The Z can decay to the right-handed neutrino or the dark matter through the neutral current interaction. And we showed that the dominant production actually comes the dark matter is can be dominantly produced from the decay of W boson and Z boson if it is kinematically allowed. So here our focus was to understand the feeble. Here actually we showed that the dark matter can be a freezing type dark matter where it is produced from the decay of the particle, and gradually its abundance freezes in once the number density of the bath particle becomes goes when suppressed.
Can I
And
can I ask a question? I have
sure,
a
sure.
question. So where is this whole scenario being enacted? Where are your steriles being produced and or decaying?
Yeah, yeah. So the steriles are being produced around the mass of the gauge bosons. Once the temperature becomes of the order of the mass of the gauge bosons, they start decaying into these steriles.
So this is happening all across the universe, early universe, is it?
Yes, but the dominant production only happens below the mass of the W boson because that's where it becomes non-relativistic, and the back reaction cannot produce the W boson or Z bosons. But another interesting point is that like these sterile neutrinos can also be produced via active sterile oscillation in the early universe. But and this phenomena was already studied by Doddles and Widrow, and they showed that like in order to explain the current relic density of the universe, what we need is an active sterile mixing which is very large, and that active sterile mixing is actually ruled out by the X-ray observation. So here we show that even so the thing is that like so we need to reduce the active sterile mixing, and we show that like with active sterile mixing with the order of 10 to the power of minus 7, I mean the square of active sterile mixing which is of the order of 10 to the power of minus 17 or so, one can easily satisfy the relic density where if the dark matter is produced via freezing mechanism through the
What is
decay
the
of
mass
W
range
boson.
of your steriles? What is the
Sorry,
mass
yeah,
range? What is the
the
mass
mass range,
range? Here,
yeah,
I
so
can't
it
see
has to
this
be
axis. What is the
ah
mass
okay, okay.
range of your steriles?
So the mass range is below 1 MeV. So few kVs to 1 MeV.
Yeah, but,
It can
but when you
still
have
have
such
a
massive steriles, they are going to go out of coherence very quickly with your active neutrinos, right? Because the
Mhm.
active neutrinos are less than EV or EV kind of thing,
Yes,
and you're talking
absolutely.
about KEV. So how long are you going to keep them in superposition, right? So that
Yeah,
is
yeah,
why I'm asking,
absolutely.
what is the scale at which, I mean, you can't expect them to survive while your universe is expanding and cooling, right? That I'm
Yeah,
not
but
quite sure I've understood that part.
so my point is that like the thing is that like this active, I mean the dark matter can also decay through it. I mean can also decay radiatively. So the point is that like once these dark matter came into picture, their abundance actually froze. Their abundance actually froze in the universe. So now the number density is not changing. It is as it is. The number density will only change due to the expansion of the universe, but not there are no other interactions that even the active sterile mixing won't change its number density. Although it can still decay to the light neutrino and photons, but the lifetime has to be larger than the age of the universe, and that's how we actually get this constraint of 1 MeV or below dark matter.
So what is your decay mechanism then?
So the right-handed neutrino can decay to the standard model photons and neutrinos through one loop. And as you can see, this one loop constitutes of W boson and the charged lepton.
And so what is the particle? Sorry, I can't see the particle being produced.
Uh,
Some myron. What do you have
no,
over
no.
there?
So in top it's photon and in the bottom it's neutrino. So the dark matter is decaying into photon and the active neutrinos, standard model neutrinos. Yeah, but the lifetime has to be larger than the age of the universe, so that it remains stable in the present universe.
Okay, but at keV, EV masses, isn't that going to be really small? There's no
Hmm.
kinetic energy, right? What is your kinetic energy? Nothing much, right?
No, no, they won't have any kinetic energy because anyway they are almost decoupled from the bath. So it can just have the energy which is corresponding to its mass.
Okay, anyway, continue. Let me see.
Okay.
Sorry, can I just ask one thing on this? I'm a bit unsure, I'm puzzled.
Mhm.
What is, you say the mixing is large, is it? Active sterile is large?
No, 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 no. So what I said was that in Doddle's and Widrow mechanism, when the
No,
sterile
sorry.
neutrino,
First of all, this is not a seesaw because you're considering a very light right-handed
yeah,
neutrino.
yeah, yeah, yeah. The seesaw will come later because this is I'm just talking about one right-handed neutrino.
So
The
the
other two,
two and three are very heavy.
yeah, they are very heavy and they can generate neutrino masses and do
Like
baryonic
we are
emission.
talking 10 to the 10 GeV or something.
Yeah, in this case, I mean, yeah, here we
If it
considered
is
a very heavy.
if it is standard seesaw, but you're saying only one of the right-handed
Yes,
neutrinos could be at the KeV scale or something.
yes, yes.
And
Although, yeah,
it is not stable. It decays, but with a very long lifetime.
yes.
And that's because the Yukawa coupling is very tiny, or what?
Yeah, so if you look at this interaction, I mean, this first column of the Yukawa matrix
Yeah.
will be responsible, is basically the interaction. This is how the sterile neutron will interact with the bath particles. And you see this sterile neutron, I mean, this interaction is proportional to the lightest active neutron mass, which we considered as a free parameter. So in order to generate correct
But
Rayleigh density,
your Yukawa coupling is tiny, right?
yes, absolutely.
We are talking 10 to the minus 9, 10 to the minus 10.
Yeah, yeah,
But
yeah.
first of all, it won't even thermalize, right? If it is so
This,
small.
yeah, this dark matter is not a weakly interacting massive particle
Okay.
where
It's
the particles
non-thermal
very
dark
little.
matter.
Yeah, it's a freeze in dark matter. This dark matter never thermalizes with dark.
Okay, because of the small coupling, the active sterile
Yes,
mixing is very tiny, right?
yes.
And then the W to N, whatever, is it tau, is it? Or what do you have? Like
It's lepton. Just I mean, charge.
any
Just
charge
the
like
charge current into it. Yes, yes,
so that would be very tiny, right?
yes, yes. That's why this abundance grows very slowly because of this feeble interaction.
Huh.
Yeah.
So it would be a freeze-in kind of mechanism, is it?
Yes, this is a freeze in dark matter.
And you can show that it can be made to satisfy the relic density, I guess.
Yes.
But then where is the observable? Is there any observable? Because everything is very tiny couplings now.
Yeah, so this is the challenge that we faced in this model. I mean, the
But
observable we can.
that N to gamma nu
Yeah.
is a very, very tiny, very long lifetime.
Yes. They
But
are they this.
none of it has any terrestrial, observables.
No,
Okay.
no. The way to probe this model is that like, if projectate or scattering detects the neutrino mass, active neutrino mass, then this model can be falsifiable because here we say that the lightest active neutrino mass has to be around 10 to the power of minus 12, so that the dark matter can satisfy the correct Rayleigh density.
Okay. But why was that initially the zero considered? What is
So by zero, I just wanted to show that if we want to decouple a right-handed neutrino, this is the best possible thing that we can do, right? Like
Yeah,
zero,
but
it
why
will just
would
fill
we
that.
want to decouple? I mean, what is there anything nice about that? Or?
Yes, because as I showed in the previous slide, two right-handed neutrinos are enough to explain neutrino masses as well as it can do leptogenesis. The question is what happened to the third right-handed neutrino? It has to be decoupled. So that's why I wanted to
Maybe
show.
it was not there at all. That's also a possibility, right?
Yes, if it might not be there, but
Yeah.
as I said in the previous slide, that the bigger symmetry demands three right-handed neutrinos. So that's why we wanted to study the cosmological implication of third right-handed neutrino. I mean, can it play the role of dark matter? I mean, type 1
So
seesaw is
you
very nice.
consider a possibility, if it is zero,
Yes,
what? Okay, all right.
yes,
Yeah, please.
absolutely.
Yeah.
Yes. So next we also tried to do. Yeah, so next we also tried to do the leptogenesis part, as I said, with other two right-handed neutrino, and we were interested in doing the flavor leptogenesis. So by flavor leptogenesis, what I mean is that the right-handed neutrino decay generates asymmetry when it mixes when we consider an interference with the tree level and the loop level diagram. The asymmetry is expressed in the following manner, which is just the difference between the production of particle and antiparticles from the decay of right-handed neutrino. But we focus on the flavored leptogenesis because, first of all, let me tell what flavor leptogenesis is. Now, consider a time in the universe when the different charge left on Yukawa came into equilibrium. That means by charge left on Yukawa, I mean the standard model Yukawa interaction of the leptons. So at certain temperature, like for example, for tau lepton, this temperature is around 5 into 10 to the power of 11 GeV. So what happens at that temperature is the right-handed counterpart of tau lepton finds its left-handed counterpart and produce Higgs. Now, if the mass of the right-handed neutrino is around that temperature, what will happen is that right-handed neutrino decays, produces Higgs and all the different flavors of leptons, like E mu tau, for example. Let us assume that they produce 10 E, 10 mu, and 10 tau. Now, at around 5 into 10 to 11 GeV, what will happen is that this right-handed counterpart of right-handed tau lepton will combine with its left-handed counterpart and form Higgs. So that means the suppose two of these tau leptons form Higgs. So what happens is that now we are left with 10 electrons, 10 muons, but only 8 tau. So this is how an asymmetry in between flavors are generated. So this is basically the timeline when the different equilibration takes place. So at around 5 into 10 to the power of 11 GeV, the interaction of tau lepton comes into equilibrium. Similarly, at around 10 to the power of 9 GeV, muon comes into equilibrium, and later on at around 10 to the power of 5 GeV, electron charge Yukawa interaction also comes into equilibrium. So again, depending on the mass of the right-handed neutrino, one needs to take the flavor effects in leptogenesis. And that's what we did here. So we considered a right-handed neutrino, the other two right-handed neutrino. And among the other two, the lightest one had a mass around 10 to the power of 9 GeV. And we solved Boltzmann equation while considering all these flavor effect into account. And we showed that one can satisfy the correct relictancy. So in this picture, we showed that type 1 seesaw can accommodate dark matter as well as neutrino mass, and it can also explain the matter-antimatter asymmetry of the universe. Now, the next question can arise is that, like we showed here, the lightest right-handed neutrino was decoupled, and there is a possibility that the heaviest might also be decoupled. So recently, I mean, the last
Can I interrupt just 1 second? So the photon will always be coupled to both the left and the right, correct?
the photons, yes.
But they will not be able to swap between left and right. They only couple diagonally.
Mhm.
The photon couples diagonally, but I'm just wondering, so you're saying that if there is initially an asymmetry, you're saying that it will persist. Is that the point or what?
No. So what I'm saying is that
So you're
the
looking at
asymmetry,
Higgs interaction, coupling
yeah.
tau left and tau right and bringing it into equilibrium and so on.
Mhm.
But the question is
So
about photons. Photons are coupled to both tau left and tau right,
yeah,
but they will not be able to change their number.
but yeah, I mean, my whole point is that, like, this process, whichever way, I mean, the point is that, like, this since tau r can couple to can produce back. I mean, when it couples to the tau l, it can produce back standard model particles. The thing is that, like, when this happens, there the co the d this as a result of this, there will exist a decoherence that decoherence among the different flavors. So there will be a washout happening in the different flavors. So this is what I just wanted to say. Even if it is photon, it will do
No,
the same thing.
the thing is about the photon, they will populate tau left and tau right, huge numbers.
Mhm.
That interaction strength is very large compared to the Higgs coupling.
Yes. Mhm.
So any such physics would be a tiny, asymmetry between tau left and tau right compared to what numbers are populated by the photon. Is that true?
Mhm. So could you please repeat once more?
No, the photon coupling to tau left and tau right is much
This is
bigger
a
than the
good.
Higgs interaction.
Yes, absolutely.
So they will populate tau left and tau right numbers,
Mhm.
huge numbers. This
Yes,
asymmetry that you're talking about at best is very tiny.
this asymmetry at best is very tiny, but yeah, but the thing is that
You're talking
even
about
that
an asymmetry between tau left and tau right, if I understood correctly. Is that
no. I'm not talking about asymmetry between tau left and tau right.
so?
What
What
I'm
is the point?
talking
I'm
is
sorry, I'm missing the point here. What is so
okay.
it is a difference between flavors tau, mu, and e,
Yes, what
but
I'm saying
not
is
to tau left and tau right, or what?
yeah. So yeah, I'm just saying is that, like, let us consider the decay of right-handed neutrino to Higgs and all the flavors, because it can decay to all three leptons, E mu tau. Now, if this decay happens around 5 into 10 to the power of 11 GeV, I mean, if the mass of the right-handed neutrino is around that scale, what will happen is that at that scale, the tau the tau leptons, the charge, this particular charge interaction actually comes into equilibrium. Now, the thing is that like uh, this decay, when the right-handed neutrino decays to all these leptons, since the bath can also produce back the right-handed neutrino, right? So there is a washout of the asymmetry. But now what will happen is that now some of the leptons, tau leptons produced in this decay, has already formed when combined with the right-handed counterpart, has already formed the bath. So now we don't have a similar number of tau lepton or the similar number of tau flavor that will produce back the right-handed neutrino. I mean,
So sorry, what
10,
what is the in the end the result of all of this? Is it
yeah, yes,
different numbers of tau, mu, and e? Is that the
ex-
claim or what? Or is
exactly.
it
So if
different
we
numbers of tau left and tau right? What is the claim?
no, no, it's the different number of asymmetry in each individual flavor. So delta
Different
tau,
number of tau, mu, and e.
yes, yes. So the thing is that
But the
one
MNS
needs,
matrix, will couple all of them, right? So the W interaction will switch between tau and mu.
but this charge current interactions are flavor blind, right? I mean, they will affect all the flavors in a similar manner.
Yeah, but they will populate, right? I mean, like
Yeah, yeah. Those those
if
things
you
are.
have an excess of tau compared to mu and e, if
Mhm.
the W interactions are in equilibrium, they will equalize all of these numbers, right?
Yeah, yes.
So then why do
But
you still say that there are different? Because that one I would imagine is more efficient, right? The W interactions are quite efficient at that epoch, so they will quickly equilibrate, I would think.
yes, but they won't be affecting the asymmetry, right? Because the asymmetry is produced from the decay of right-handed neutrino,
Yeah,
which has to
initial
evolve
asymmetry
into.
will be quickly washed out, is all I'm saying. Because the weak interactions are in thermal equilibrium.
Mhm.
Just the standard weak interaction will thermalize all of them, no? Will equilibrate all three of them.
Yes, but the asymmetry will still persist, right?
Yeah, I don't see. Maybe you should continue. We can come back.
Yeah.
Yeah, yeah, sure, sure, sure. Yeah. So I mean, so if we decouple the third right-handed neutrino, what will happen is that there is a chance that it might dominate the energy budget of the universe. Now, so if I consider the third column to be zero, and then just perturb it in a very small amount, what we showed was that it can dominate the energy budget of the universe, and it can at certain point of time, and era of early matter domination will be induced. So as a result of which, the expansion rate will change, as you can see from the expression of the Hubble rate H, and the it also contains the energy density of the right-handed neutrino. And if that happens, what it will do is that now the expansion rate of the universe has changed. So the equilibration temperature that I was talking about in the previous slide will also shift because the expansion since the expansion rate is changed. So as a result of which, if you see this plot, the solid lines corresponds to the interaction rate, gamma by the ratio of gamma by h, where gamma is just the interaction rate, the charge current to gamma interaction rate of the different leptons. So by blue corresponds to the equilibration of tau, mu corresponds to the equilibration of green corresponds to the equilibration of mu, and red corresponds to the equilibration of electron. And see, this all these happens at a different stage. Now, if this early matter dominated era existed, the expansion rate will change, and as a result of which, this equilibration will be delayed, as you can see from here. There is a shift towards the lower temperature. Now, this shift can be almost can be as large as of the order of one. As you can see, the equilibration temperature for tau, as I showed in the previous slide, was 10 to the power of 5 into 10 to the power 11. And here we see that it can shift to 10 to the power of 10, 4 into 10 to the power 10. Now, as a result of this, even if we have the right-handed neutrino mass, which is 10 to the power of 11 GeV, we can still work with unflavored lipidolysis, and we don't need to consider the flavor effect into account.
Hi, just
Now,
one question. When you add this early matter dominated era that you sandwich between two radiation dominated era, right? In that
Mhm.
case, do you expect any changes in the Hubble parameter? Does it change?
Yes,
Uh,
yes, as you can see from here,
uh-huh. And no,
because
what I'm asking is that at the today's Hubble parameter, how does it change? Whether
it
it goes, towards solving the H naught tension and things like that, or not?
no, it won't be able to solve it because you see, at once the right-handed neutrino, the third right-handed neutrino decays, the universe again becomes radiation
No,
dominated,
that is fine.
and
If you
yeah.
remember this, there's this early dark energy people have explored where you have a dark energy that was sandwiched between this radiation dominated era. That means that it
Hmm.
is pre-recombination time around redshift 10 power 5 or something like that. So probably
Hmm.
your thing is much earlier or maybe
It's much early. It's
much earlier. Okay,
much
okay.
earlier,
Then
much
it might
before
not.
these
Okay,
events.
okay. So, but
Yes.
I was trying to guess whether it will change or not because if you because at that point of time the dark energy has the equation of state of the early dark energy has the equation of state
Yes.
of 0.5.
Hmm.
So which is not even like a negative equation of state. So
Right.
if you sandwich this between them, even if they decay down, okay, early dark energy
Hmm.
also basically flatlines and goes to the cosmological constant at the later epoch. But
Hmm.
even if it is decaying down, it will leave an imprint at that epoch. It might change the RD, the
Hmm.
drag epoch, the baryon drag epoch,
Okay.
etc. So have you checked whether it changes the RD or this kind of uh,
Uh,
baryon markers?
no, in this work we did not because
Okay.
because this matter domination happened at the much earlier stage, much earlier.
What is the redshift? A typical redshift or?
So this is this. I mean, as you can see, the temperature of the universe is roughly around 10 to the power of 14 GeV or so because
Oh,
the
okay,
mass
okay, okay. The guts.
it's
Okay, I understand.
gut scale. Yeah, it's very early.
Okay, thanks.
Yeah, yeah.
And
So this,
hello.
yeah,
So you
yeah.
use this expression of mh squared as a function of t. So
Yes.
for this, what do you use?
So we just use approximate relation, which is around zero point 0.6. I mean, this is just a thermal mass of X, which we consider around, which is proportional to T square, and the
T
coefficient
square.
was around. Yes, MH, MH is T, and MH square will be T square, right?
But there is also a coupling sitting there.
Coupling. This white tau.
No, no. In the MH, there is a
Yeah.
coupling.
So in MH the coupling will be there. So that's why I mean when if we try to consider the thermal mass of the Higgs, all the couplings are basically in that coefficient. All the couplings are actually coming. So we
Which
need to
coupling do you
go.
use? I wanted to ask.
So the gauge couplings will be present.
Which specific coupling do you use?
So in this case, like since the W boson, the gauge bosons can contribute to the thermal loop corrected Higgs mass. The Yukawa interaction can also contribute to
W
the.
bosons are massless at this.
No. I'm talking about the loop mass. So even Higgs is massless at this stage. This is the thermal mass of the Higgs.
That is fine, but that is proportional to d by mass, which is g times t.
Yeah, so it's basically the gauge coupling.
G is
Gauge
very
coupling law.
small, tiny at this. If you take the electroweak coupling, that is extremely tiny at this energy scales.
Yeah, so I mean, yeah, and so that's why, like, if we take the cumulative effect, this magnitude, what is, I mean, is roughly around zero point 0.6. I mean,
And of course,
even
now the next question comes is at these temperatures, if Higgs is coupled to some other massless beyond standard model particles,
yes,
then that
that will
number
also
can be
contribute.
large.
Yeah, that will also contribute. That will
Because
also contribute.
as you know, d by mass is the only leading order effect. The next to
Yes,
leading order effect is non-perturbative.
yes,
In
yes.
QCD,
So,
that is 100% of the leading order correction.
mhm.
So I am now a little bit perplexed with this relation. So
Oh, okay. Yeah, I mean, here the idea was just to show that like this effect can change the equilibration temperature. Yes, I mean, if we do consider we just use this approximate relation, but if we do I mean, we consider all the leading order and next to leading order corrections in the Higgs mass, this thermal mass will change, and this might shift
No, no,
slightly
even that
the
leading order, that is not the point. I mean, see, it is not proportional to t square is a meaningless statement because the coefficient tells you how large or how small it is, right? Because
yeah,
all
yeah,
bosons have the same t square dependence, right? Well, so
absolutely,
do
yes,
fermions also. But
yes, yes, yes,
the coefficient is what matters, right? I
yes,
mean, that's what
absolutely,
decides whether this is going to be significant or not,
yes,
right?
yes, yes,
So
absolutely.
what diagrams are actually, when you say gauge boson, what is the diagram you're thinking of?
So I can think of M in the loop you have W's and then it again connects to M. So this is yeah. So it's a kind of self energy diagram. Then one can think of interaction with top as well. Top one. Okay. Try to,
Okay, anyway, sorry, proceed. We'll worry about it later.
yeah. So I mean, here the idea was that like the presence of this early matter domination can actually shift the equilibration temperature, and then it can affect the leptogenesis parameter space. In another work, we showed that a similar effect can be observed if we consider a delayed reheating. That means that the reheating of the universe was not instantaneous. So when the interton roll down its potential, it starts oscillating and it reheats the universe. So here we considered that the interton actually couples to the standard model fermions, and notice that this coupling has to be ineffective, so it has to be small. So the interton decays and produces the radiation bath, produces the bath, thermal bath, and in that process, during the process of reheating, the right-handed neutrinos were also present because they can be produced in that phase as well. And then they decayed and produced the asymmetry. But again, here the expansion rate was modified because of this non-instantaneous reheating. And as a result of which, the flavor effect again shifted. The flavor regime or the equilibration temperature again shifted. And as a consequence of which, the leptogenesis parameter space was affected, as you can see. Now, with the shifted equilibration temperature, the parameter space is actually bit shrink. The shrink, which is actually shown by the blue dots. So this was some of the work that I did in the field of early universe, where I tried to provide an explanation for the matter-antimatter asymmetry, production of dark matter in the early universe, and the neutrino masses. Now, the question is that, like, whatever I have said so far, all of these involve very high scale. So, is there a way to probe all these high scales? So, the answer is yes. Maybe gravitational wave can help us understand the early universe, as I showed in the earlier slides as well. So, here I'll talk about my contribution, where I tried exploring the gravitational wave signature during the reheating era. Another thing we tried was to I tried to understand the gravitational wave when it is generated between the reheating and the BBN era. So to start with, uh, I already showed this diagram in the previous slide. Here it is interesting to see that like the gravitational wave can also give us information about the inflation if it happened. Yeah, exactly. It can also give us information about the inflation. It can give us information about the inflation, the reheating phase, even the radiation dominated phase. I mean, because different universe could have gone through different phase transition, or different processes might have happened in the early universe that could actually generate gravitational wave. So in the next work, which I would like to show, is that we tried to explain. We did leptogenesis during the reheating era, same as the work that I showed in the previous slide. But here we consider the generic equation of state for inflaton. So I don't know if it is feasible. So yeah, so this we consider a generic equation of state for inflaton and a generic inflationary potential. Now, and just for the purpose of demonstration, I just considered the so inflaton. So the if you consider an inflaton potential with 5 to the power of k, here we just consider k to the power k equal to 6. We showed it for k equal to 2, k equal to 4 as well. But this is just a demonstration. This is just for a demonstration purpose. Now, for k or equal to 6 scenario, the universe gets reheated at a very late stage, because here you see the radiation becomes equal to the inflaton energy density, and this process The right-handed neutron also decays and generates asymmetry, but the final asymmetry is also determined by the reheating temperature because of the decay of inflaton, it introduces or injects the entropy in the bath, and that actually dilutes the asymmetry produced from the right-handed neutron, and hence
Rishabh,
it yeah.
when you're mentioning reheating,
Mhm.
and also you're mentioning particle production. So as far as I understand, the initial particle production is non-perturbative.
Yeah,
So
yeah.
which phase are you referring to here?
So it's the final phase. So I'm not talking about the preheating, but I'm talking about the last phase when the inflaton decays, and the it can be non-perturbative if the couplings are very high. So here the choice of coupling that we took was not that high. It was around 10 to the power of -6 or -7, for around -10 to the power of -5 to -6, so that it still remains perturbative. So we consider the perturbative reheating.
Yeah, and then what uh, means you have these leptogenesis happening on this scale. So how do you decide which one are the non-perturbative ones? And this is model dependent in your case.
This is model dependent. So as you can see, the type 1 seesaw interaction that I showed earlier was responsible for leptogenesis, and that couplings are significantly, I mean, way smaller than order of one. But this coupling, the interton coupling to right-handed neutrinos, as you can see here, is of the order of 10 to the power of -6 or -7, which is extremely small. And similarly, this inflaton coupling to the standard model vase is also very small. So we do not enter into a perturbative regime. And going into a perturbative regime is a good idea if we increase the coupling size. But in that case, one cannot rely on the Boltzmann equation. One needs to do the lattice simulation and then try to see what happens. So this is another thing that right now I'm working with some of my collaborator. I'm trying to understand this nonlinear dynamics.
And
But
what
again,
fraction of your inflaton fields have decayed already and what is there at this stage?
so at this stage, like when the universe was created, the inflaton was completely gone. So they were completely decayed away.
Okay, and when this process starts, then how much is your fraction?
It's that we can, I mean, when this process starts, it's the inflaton energy density that actually dominates the energy, but
But that
it's
is the
not just.
precise region where your non-perturbative effects are very dominant.
Yes, but again, the coupling, since I mean, we considered the coupling to be very small, and again, this is a very approximate result. I mean, one needs to properly do this lattice simulations, and that is what I am trying to learn now. This was, I mean, because we were using Boltzmann equation, and it is very approximate, so one needs to properly consider the
Thanks.
nonlinear dynamics.
Sorry, just one question. So here the inflaton couplings, does it matter at all? I mean, like the final state will not thermalize, is it? Like the N and F and all that. After the decays, it won't thermalize?
No, no. So the thing is that like after the decay, n will anyway won't be present because the mass of the ends were pretty heavy, quite heavy in this case, and the bath will thermalize once the interton
Sorry,
decay has completed.
the reheating scale is below the mass of the N or what?
Yes, the
So
reheating
that's
scale
an
is below the
assumption
mass.
or what?
Yeah, in this case, this is an assumption. We were trying to focus in this scenario where the right-handed neutrino masses were heavier than the reheating temperature or larger than the reheating temperature.
I see.
Yeah.
So what N are you imagining? The mass of the N that
Uh,
you're
It, it, so here we were considering around 10 to the power of 11 GeV, but the
and the
reheating
reheating
temperature
scale?
was a bit low. Reheating temperature was much lower. I mean, yeah,
Okay, just to see what happens, is it? There is no reason
yeah,
for.
exactly.
Okay.
No, there is no more reason. We just wanted to analyze this possibility.
So if the
One
reheating
can,
scale is very low, then you will not initially populate the N.
no. So if the
And
reheating temperature is very low, so uh, these ends can actually be produced. I mean, here we considered that it can also be produced from the decay of inflaton. So the ends can be populated from the decay of inflaton as well.
wait,
So
I'm
they can
confused.
slowly.
Now, I thought you said that the temperature is below the mass of the N.
The temperature is below the mass of the end, but inflaton mass is very heavy, right? So it can decay and produce. It's much heavier than the right-handed neutrino mass, and it can decay and produce right-handed neutrino as
Yes.
well at the time it was producing the bar.
Okay.
But when the right-handed neutrinos came into picture, they were simultaneously decaying as well to the standard
Okay.
model electrons and
So they
generating
are
this.
out of equilibrium and they just decay.
Yes, absolutely.
And they
So there
produce
are,
asymmetry, is it?
yes,
Okay.
yes. So, so we did a similar analysis that I showed in the previous slide. So here the idea was to see if we can get some information about the early universe using gravitational waves. So, uh, yeah. So the first gravitational wave that we can think of is the one that appears during the inflationary phase, that is the tensor perturbation. Now, during the inflationary phase, one can think of tensor perturbation, which is the perturbation in the space-time matrix. And then what happens is that during the phase of inflation, the expansion happens exponentially. So these perturbations can be stretched. Now there is a chance that these perturbations can cross or might be larger than the horizon scale, as you can see from these small diagrams. I don't know if it is visible properly or not. But as you can see, these perturbations can be larger than the horizon size. And if that is the case, these perturbations will freeze in time. And later on, once the expansion, since the universe was already expanding, there is a chance that this fluctu so these fluctuations might again re-enter the horizon. And once they have re-entered the horizon, they can evolve and we evolve redshift and then we can observe it today in the present time. So in such a scenario, the primordial, the gravitational wave amplitude actually depends on the primordial tensor power spectrum, which is denoted by this. And here R is the tensor to scalar ratio. P zeta is or P xi is defined as at a pivot Planck scale, which is just a reference point. NT is the tensor spectral index. In this scenario, we consider it to be 0. Now, if you just look at this expression, what we see is that P xi is of the order of 10 to the power of 9, 10 to the power of minus 9. On the other hand, uh, omega photon is of the order of 10 to the power of minus 5 with h to the power of minus 2 gives us around 10 again 10 to the power of minus 9. So this tensor perturbation or this spectrum originated from the initial phase, the total value will be very small and it is roughly of the order of 10 to the power of minus 17 or so. So as you can see from this plot, so this horizontal line actually corresponds to that power spectrum and the amplitude is very small. So in this work, we showed that like if we have a different equation of state, that means that the equation of state is bit stiff, which is if it is larger than k equal to 4, what it can do is that it can enhance the power spectrum. It can and one can see a blue tilted gravitational wave phase as you can see from the figure on the top. So here we considered again, as I said, different powers of inflationary potential, and we chose our couplings in such a way that the reheating temperature for all these scenarios remains same. So we studied this for k equal to 4, k equal to 6, and k equal to 8. And this shows a blue tilt, which is not which we won't observe in k equal to 4 scenario or in the standard scenario. But if we go for a stiffer equation of state, we see there is a blue tilted spectrum.
Rishabh, the blue tilt only picks up at a very small scales and right, or it is not visible in at any point in the CMB scales.
No. It actually this blue tilt happens at a very high scale. Yeah, I mean
Very
at a very large
small scale.
frequency. Yeah, a very small scale. I mean a very large frequency. Yeah, now
Because
also
you are
depends on the
setting
reheating.
NT to be 0,
Yeah.
then your model is allowing NT to be 0 for a long time, and then the blue tilt kicks in at a very late time, after the inflation, and sorry, at a very late
No,
stage
no.
of inflation. Sorry, very
Yeah,
late stage
yeah.
of
So,
inflation. Yeah.
so this is the maximum amplitude. I mean, this is the maximum of amplitude is obtained when the inflation actually ends, and then this is the reheating temperature. This is the spectrum at reheating temperature when the universe is reheating.
Okay.
So different modes actually can enter it at a different rate.
Uh,
Some modes can enter at the time when the inflation ends. Some modes can enter at the time when the reheating happens. Some modes can enter at a much later stage. So
I understand.
the modes that enter much later stage won't show any effect actually.
Do you have any other, for example, can you this NT, this blue tilt, can you distinguish it with respect to the scalar induced gravitational waves that people work on?
The scalar induced gravitational wave, the scalar, yeah, I mean the scalar induced gravitational wave will be. I need to think.
It
I've
will have a
not worked
scalar
on it.
signature. I'm not talking about that. It
Yeah,
might
yeah,
create primordial black holes, but in the
abs-
GW spectrum, do you
yeah,
have
yeah.
any litmus test kind of thing that this is not coming from the scalar induced, but from your model or something like that?
This is actually an interesting question, and I have a slide for this at the end of my talk. I
Okay,
mean, this
I'll
is
wait.
a very important question. Yeah,
Okay,
yeah, yeah.
I'll wait for that.
Maybe I'll discuss it maybe after a couple of slides.
Sure.
So yeah, so let me move on to the next slide. And
Sorry,
because we,
can
yes,
I? So this is a
yes.
blue tilt in what spectrum?
I mean, at a very high frequency. I mean,
So what,
around
like, is it, what spectrum are you talking about?
what spectrum means?
Is it matter power
It gra
spectrum or is it like
no, it's a
gravitation?
gravitational wave.
And the reason for it is what?
So the reason for it is that like as if we have a different equation of state, what it can do is that uh, as a result of different equation of state, the the reheating temperature is changed, the time at which the inflation ends will change. So the different modes can enter into different
I see.
modes will
Okay.
enter.
All right. Okay. Yeah, got it. Thanks. Yeah.
Yeah, so even if you look at this expression, maybe it's very tiny. If k is equal to 4, you won't see any tilt actually. If k is larger
Great.
than
By
4,
the way,
you will see.
your equations are so small here we cannot see
Yeah,
anything. But it's
yeah,
okay. Yeah, yeah.
I'm so sorry about that. Yeah, yeah, I'm so sorry.
It's
I
okay.
just
Yeah.
wanted to present this picture. Yeah,
Okay. All right. Please
yeah.
continue.
So
Yeah.
okay, so in the next slide,
Rishabh,
yes, yeah,
actually, we are already 1 hour past. I understand there are many questions, but if
yeah.
you can actually speed up in another 15-20 minutes, that would be
Sure,
great.
sure, absolutely. I just have two,
Thanks.
three more slides. I mean, not two, three, but I have some slides, but I'll just quickly go through it. So in the next slide, I just wanted to show that like what will happen if a PBH is also present during the reheating phase. So if that happens, the PBH can evaporate and produce gravitational wave, which whose spectrum looks like this. So this is another work that we did recently. In this case, the dominant production of gravitational wave happens at the time PBH evaporates. Then, since the inflaton was also present, it can scatter and produce gravitational waves. And this is the typical spectrum that we get. Now, the third source is also the PBH. As I said, like earlier, that the distribution of PBH can also generate gravitational wave and introduce quadrupole moment. So in that case, like one obtains this scalar induced gravitational wave. So in this work, our idea was to cover all the possible sources that can generate gravitational wave and see the different gravitational wave spectrum. I mean, there could be other sources as well, like PBH mergers and other things, but like here we did not consider those. Here we just wanted to focus on these peaks. Next, uh, yeah. So next, I want to briefly go through the reheating era in between reheating and BBM. So in this phase, several things can happen: particle production, matter antimatter asymmetry. All these things can happen. Even there can be a breaking of some spontaneous symmetry like discrete or continuous. They can lead to the formation of topological defects like domain walls, cosmic string, where non-standard cosmologies can exist. So, so I'll briefly go through what will happen if the domain wall annihilate and how it can generate gravitational wave. So domain walls are topological defect, two-dimensional topological defect, which is which are formed when a discrete symmetry is broken. Now, interesting thing about the domain wall is that I mean the domain. First of all, the domain wall dynamics is governed by its tension. An interesting thing about domain wall is that energy density dilutes very slowly. As a result of which, it can dominate the energy budget of the universe, which is a cosmological catastrophe. So there is a way out. What people do is that they introduce an explicit breaking term and introduce a bias between the potential and breaks the degeneracy. As a result of which, what happens is that the domain wall starts annihilating and it can generate the gravitational wave spectrum that looks like this. So the initial phase, the domain wall changes its shapes and it releases energy. A peak is reached when the pressure force and tension force becomes equal for the domain wall, and later on it annihilates. The interesting, the important point is that the later part of the spectrum is not very well. It contains a huge amount of error because we actually don't know how the domain wall, if they existed in the universe, how they would have annihilated. Now we
Rishabh,
can.
sorry, what is the origin of this spontaneous symmetry breaking? This
So,
is
so
which epoch are you talking about?
So this is I mean I'm just saying that like if we are in the radiation dominated era after the reheating, so there might be, I mean we don't know that there's a possibility that several symmetries might have broken. They might have existed in the early universe. So here I just show that like if there was a discrete symmetry which was spontaneously broken, that could lead to the formation of this kind of topological defect.
So these are
Similarly,
this is your Higgs fields or what is what?
this is just I mean just consider a scalar singlet extension of the standard model who's
But
who the
those we
and
understand that they're severely constrained. There are other observations which rule out all these domain wall things and cosmic strings very strongly. These are all
rule out in which I mean it
means
should
they
not
are very there are very tight constraints on those, right?
yeah. So the
There
thing
were
is that
models
like
by Frank Wilczek and all, and those were very tightly constrained.
yeah.
Constrained.
So the constraint comes from actually the CMB and BVM. So this even if these kind of topological defects existed in the early universe, they should not affect the CMB constraint, the CMB bounds. So that's why we don't want this domain walls to exist in the early universe. We want them to vanish actually. That's why we introduce a bias term, and as a result of which it annihilates, and it annihilates much before BVM. And during this process, it can actually emit gravitational waves. So this
And
is
sorry,
the one.
so in which scenario are you looking at this domain wall formation?
In which scenario? Here I just wanted to show that if there's an additional scalar that was present in the early universe, apart from the standard model Higgs, whose that also preserves the Z2 symmetry. And if that scalar obtains a vacuum expectation value, or in the other words, if that Z2 symmetry was spontaneously broken much before the electroweak symmetry, then it could lead to a formation of domain.
Okay.
Yeah, and it can generate gravitational waves. So in one of our work, we tried to connect it with leptogenesis and dark matter. Here we had a scalar that couples to the standard model neutrinos, standard model particles and right-handed neutrinos, and it also couples to a dark matter chi, which is feebly interacting. And as I discussed earlier, the decay of right-handed neutrino generates uh, the matter antimatter asymmetry, whereas the in this case the phi decay generates the chi dark matter, and it was a feebly interacting dark matter. So I mean here we chose symmetries in such a way that the Dirac mass term can only be written at a higher dimension operator at a non-renormalizable level, as you can see from here. So in the plot at the bottom, we showed the region of parameter space in the mass of the scalar plane, which is m phi, mass of the scalar, and the breaking scale plane. And here the solid line corresponds to the region of parameter space where one can obtain a correct relic density for different dark matter masses. The dots and star corresponds to the benchmark points where the correct baryon symmetry can also be observed. And the dashed line corresponds to all the dashed line corresponds to the sensitivity curves of different gravitational wave experiments. So here we in this model actually gave us some idea about is it possible to prove or understand at least the breaking scale of this symmetry if it existed in the early universe. Maybe I can quickly tell you about another work of mine where we tried to explain the nanograv results from the domain wall annihilation, and we showed that since we know that gravity does not respect any global symmetry, including the Z2 symmetry. So quantum gravity effects will break the discrete symmetry. Simultaneously, it will also break the discrete symmetry that stabilize the dark matter. It generates it annihilates the domain wall annihilates and generates the gravitational wave. And the dark matter, as a result of which, also decays, and this decay has a is significant. The lifetime of the decaying dark matter is significantly constrained from the CMB. So here, our idea was to explain the nanogram result and also get some idea of the scale of quantum gravity. So let me just briefly tell about one more work where I wanted to show that how cosmic strings can come into picture. So cosmic string appears into picture when a continuous symmetry is spontaneously broken. So this is a topological defect which actually stretches with the time, and it also intersect among each other, intercommute among each other, and as a result of which cosmic loops are formed, small string loops are formed that actually radiates and generates gravitational wave. And this is the typical spectrum of the gravitational wave obtained from cosmic string. It increases and then it saturates. So in one of our work, we tried to probe an early matter dominated era if it existed in the early universe. So here we had a UN gauge symmetry that was broken that led to the generation of cosmic string and hence the gravitational wave. Here we also considered that a PBH was also present in the early universe. So if the PBH evaporates, I showed that it can induce a scalar induced gravitational wave, which has a peak. So if that happens, if this was present in the early universe, it would have given an imprint. It will give an imprint on the gravitational wave spectrum of the cosmic string. So this was all about the work that I did to understand the gravitational waves coming from the early universe. Now I just quickly want to tell you about the current status, my ongoing work, and future direction and outlook and synergies with the department. So the question raised by Deepak was very important because we face this degeneracy problem. What is the degeneracy problem? That means if we follow a bottom-up approach, that means that like if we observe a gravitational wave spectrum, can we pinpoint the source from which it is coming? So this is basically the degeneracy problem. So that means different origin might have similar spectra, peaks can be at same place, multiple source will be adding up. A simple example is the nanograph results that we saw recently. And as I said, I mean, domain wall can explain nanographs, cosmic string can explain nanographs, scalar induced gravitational waves can explain nanographs. But then the question one should ask is that can we actually pinpoint at the source? So can we distinguish one source from another? What if there are multiple sources present in the pre-model pre-model mechanism that would have operated simultaneously? So the way out, what I consider is that this should be our approach. Either we need to look for a distinct feature in the gravitational wave signal, like multiple peaks or spectral breaks, and on top of that, we should also look for a complementary signals at different frontiers like dark matter experiments, neutron experiments, collider searches. So the in goal is to look for a multi-messenger integrated approach. I mean, one should think of a model. So one needs to build model in such a way that if it generates gravitational wave signals, that model should also be probed by other experiments. So I've already started working in this direction where I'm trying to see a twin peak gravitational wave spectrum coming from discrete symmetry breaking. With Jose Valle in IFAK, I'm trying to correlate the gravitational wave spectrum and lepton reverse signals in low scale linear seesaw model with my collaborators at Southampton, Alexander Belayev and Alfonso Zurich in Chile. We are trying to understand the minimal scale invariant WIM type dark matter that can generate gravitational wave signature, dark matter searches and collider searches. And on the other hand, with some of my collaborators in Southampton and some of my Indian collaborators, we are also trying to probe low scale lepigenesis with ship experiment. So this is my research goal. On the short term basis, I would like to test some of my theories with gravitational wave and particle data. As I showed earlier, that it's very difficult to probe such high scales. I also want to probe low scale leptogenesis. I want to see how gravitational wave spectrum will change if there are multiple or if there are hybrid defects. That means one defect is connected to another topological defect. In long term, I would like to connect this PBH formation community with the PBH evaporation community because for some reason they do not interact among each other and they do not interact among each other. And because since both of these are a good source of gravitational wave, I would like to unify inflation, dark matter, baryonos emitting neutrinos in work, and then I would also like to understand if gravitational waves can reveal the particle nature of the dark matter. I would like to build models that will guide future experiments. Now, we are at a very interesting phase because in the upcoming years we will have LISA experiments that will be working. Then we will have ETC by 2025, 2045, and this can open the window in, and we can look into the early universe. It can tell us about the electroweak and dark sector phase transition or the other early universe phenomena. Now, as I said, we need to systematically build our models so that it generates gravitational wave. We need to look for complementary searches. Then there are open frontiers that we still need to figure out, like model degeneracies, theoretical uncertainties, etc. But at the end of the day, what I would like to say is that the next 2 decades will either detect remodel gravitational wave or place a transformative constraint on the BSM scenarios, and either outcomes will revolutionize our understanding of early universe. So, as I said, like I have a good overlap with the research in the physics department at the Indian Institute of Mathematical Sciences, as I showed earlier. But on top of that, I'll also bring my expertise on gravitational wave premodel black holes. Although I did not discuss in recent works, we have also showed that relic neutrino, decay of relic neutrino can solve some of the cosmological tensions. So, with me being a part of IMSC, I will help us expand the research frontiers. So finally, I would like to conclude by saying that gravitational wave encodes the dynamics of early universe. It provides windows much beyond LHC. And as I said, early universe mysteries might likely be hidden in the BSM physics, and gravitational wave gives us indirect access. It can uniquely access the pre-recombination era, and with the upcoming or next generation gravitational wave detectors, we can actually either detect or exclude a huge range of BSM models, which will be very interesting. And actually, in order to do that, we also need to follow a multi-messenger approach. So the key takeaway is that gravitational waves cosmology is actually one of the most promising avenues for the discovery of beyond the standard model physics. So in this talk I did not mention how relic neutrino decay can solve cosmic anomalies. I also did not. We did some work where we tried to understand iron dark matter and its connection with leptogenesis, and some of my other works. So yeah, thank you. I'm sorry if it was a bit long.
Rishabh, one question
Yes.
on the domain wall, like
Yes.
the Z2 broken domain. Like, first of all, can like Higgs domain walls exist, or what is the situation?
Higgs domain wall can Higgs domain wall. So the thing is that like if SU, I mean domain walls exist when a discrete symmetry is broken.
Yeah, but we have this U1 in the case of Higgs, right?
So, but U1 is a continuous symmetry, right? So
Yeah, so
that can actually generate cosmic string.
yeah, but not a domain wall, right? So
Not the
there can
domain.
be Higgs cosmic strings. Is that what you're saying?
Yeah. I'm saying that like since SU2 U1 SU2 across U1 is broken,
Yeah.
the gauge symmetry, this is the continuous symmetry which is broken. That can lead to the formation of cosmic string. But since this breaking happens at a much later stage, this cosmic string won't be able to generate. I mean, it can generate gravitational wave, but it won't. That gravitational wave signals will be very weak. The
Very
breaking has,
weak.
yeah, very weak. So it won't be. We won't be able to detect those
Why
signals
would it be very weak?
because the string tension will be very weak because the string tension actually depends on the breaking scale. Now,
Sure.
if
Yeah.
we want, yeah. So I mean, the scenario that I discussed, that
But
string
but
tension was
but it
very.
is later in the in the time scale of the universe. So then will
Yeah.
that matter? So the fact that it's not as redshifted, perhaps.
It won't be as redshifted, but the amplitude. I mean, even at the
Yeah, the
time of
amplitude
production,
will be small. Yeah.
very small. Yeah, but and with the redshift, it will keep decreasing, so
But
it
the
won't be very.
frequency would be in what frequencies? If you take the electroweak
So,
break.
so it will be roughly around LISA scale, I think.
It
frequency
will
range
still
of
be in the
Lisa.
Lisa scale.
Lisa scale, but I'm a bit unsure about the amplitude. I think the amplitude will be very small.
No, this is not the question of amplitude, but about the
Yeah,
frequency.
the frequency will be around the Lisa scale.
Around Lisa scale, is it?
Yeah.
Sorry, what is the frequency range like? Is it in, did you say it is in the Lisa scale or what? I missed what you
Yeah,
said.
I said Lisa. So
Okay.
Lisa, so as you can see from here, the Lisa is in millihertz. So like it can actually tell us about, give us information about the electroweak phase transition around this.
Okay. But the amplitude will be very tiny.
Yes, that's what I
Okay.
expect.
Okay. Thank you. Yeah.
Sorry, you mentioned it can give us a hint about electroweak phase transition,
Mhm.
but we know that it is a crossover. So how will there be effective coupling with the gravitational waves?
So the thing is that the electroweak phase transition, if it is, I mean, so we know that the electroweak phase transition is not of the first order. So if there is a beyond the standard model physics, and if we can make it of the first order, then the first order phase
How will we
transition
make
will,
it as a first order? Because we do not know any standard beyond standard model particle with
yeah,
couples at these energy scales. So I don't
right.
understand how will you make it first order in this scenario.
No. So if there is no beyond the standard model, we cannot make it first order. But at the
But
when the
from
electroweak,
LHC, we know that at these scales there are no BSM particles. So how do you
yes,
anticipate?
yes. So the important point is that uh, even if it is not first order phase transition, this could give rise to the cosmic string, right? As I was saying, and that could actually emit gravitational waves, and we need to calculate the amplitude of the gravitational wave and see if it is if it is if it will lie under the sensitivity curve of Lisa or not. But
But
we need to do that
these
calculation.
cosmic strings and all, these are all gauge dependent quantities.
Yeah,
So
but
you're assuming some gauge, you're assuming some solutions of these. So how do you connect it to any physical quantities?
yeah, so I mean, so when you talk about the electroweak phase transition, the only symmetry was the SU2 cross U1, right? So when the symmetry was gauged, that would also lead to the formation of this topological defect, which was cosmic string. The thing is that that will appear in the nature,
Yes,
and
I can
that
understand
in
there
the,
can be
yeah.
instantons and all, but how are instantons are gauge independent objects and you can write a solution. But these
Mhm.
cosmic strings and all, these are all gauge dependent solutions. So how do you connect it with the gauge independent solutions? Is why do people look at these kind of objects, right, which are gauge dependent? Then your everything becomes a gauge dependent statement, and then your cross
That is
section
true. Yeah,
everything.
that's true. That's why like we need to do a very, I mean, we need to do a systematic model building. So that's these are the challenges that we face right now. So I
And also
mean,
electroweak instantons are very suppressed because the
yeah,
sphalerons, the
absolutely, absolutely,
yeah.
absolutely. Yeah. So these, I mean, that's why I said like these are the challenges that we are facing right now, and we need to work a lot in this direction.
Yeah, and another question I had was regarding your scalar fields, Z2 scalar fields that we were
Hmm.
discussing. So these
Yeah, yeah.
scalar fields, do they couple to the inflaton, or these
No,
are
no.
independent ones which are produced in the preheating stage?
Okay, these are independent ones which are produced in the reheating stage.
The reheating stage.
I mean, not reheating stage, after reheating, once the universe was already reheated. We just considered if this scalar field was present and if this
Oh, these are
symmetry was
not produced from the inflaton. So these are
no,
like,
no, 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 at a much later stage, after reheating. We just wanted to present this scenario.
and if I may ask, how do you, is there any way in which one can constrain the most probable BSM scenarios? Because there may be many such scenarios and
Yes,
many such possibilities. So
yes.
can the gravitational wave signals help you to constrain it like realistically? Like
Yeah,
put a constraint on the BSM models?
yes. So that's so if you look at this slide, I mean, this is the biggest challenge that we face right now, the degeneracy problem. That means that if we detect a gravitational wave signal, can we pinpoint the source? And this is the
Yeah.
challenge that we face right now. So we cannot. The only way to pinpoint the source is that if the model gives also if it also gives another signals apart from the gravitational wave signal. So I think this is the thing that we need to do in future.
Okay, thank you.
At the current status, we cannot pinpoint the source.
Okay,
This is the
thanks.
current status.
Yeah.
Yes. Thank you.